the memory complexity or the space complexity of a function is the memory taken by the function when the function is executing. We have already seen the memory model of factorial function in the previous program. Let us take one more example. Let's say you are given an array and the array given is 5, 6, 7, 8, 9. And we want to print this array. If we are using Java language, then the function for printing the array will be like this. Even though in Java, we do not need to pass the length of the array, we are receiving array and the length, and this function is printing all the elements of the array from the first element till the last element. Now, if you are coming from the C++ background, you may find this static confusing, but because we are calling it from the main function directly, we need to have this function defined as static. In the main function, we have this array. This is the same array 5, 6, 7, 8, 9, and then we call the function print array to print the array. If we run this program, then the output will be 5, 6, 7, 8, 9. Let's put a breakpoint and let's debug this code. The memory taken by a function can be clear from the call stack of the function. The memory model that we discussed in the previous video is nothing but the call stack of the function. The first function which will get called is the main function. So we have the stack frame of the main function here. And if I do a step over, we are on the second statement of the main function. And if I do a step into, now we are in this print array function. In the print array function, there are two local variables, arr and n. And there will be third local variable I. So if I move to the next statement, then I is also there. Initially I is 0, system.out.print. System.out.println is equivalent to cout in C++ and print in Python. Initially I is 0, then value of I is 1. It will print the first element. So 6 is getting printed. Value of I is 2 now. You can have a look here. So here I is 2, n is 5. If we go further, then value of I has become 3. Now value of I has become 4. Value of I then becomes 5, and we move out of this function. Now when we move out of this function, you will see that this stack frame will get deallocated and the control will come to main. The stack frame of main function is already present in this memory stack, in this call stack. It is only suspended and the execution is suspended at this point. So if I do a step over, now the execution control has come to main and then it will stop. Okay. If we draw the diagram of the memory model, then this is the diagram. So you can have code area, data area. These are discussed in the previous videos. First, the main function is called. So we have the stack frame of main. Here, memory will be allocated to the local variables of the main function. Then main call the print array function. Print array function. So print array function has arr. It has n, which is equal to 5, and it has I, which is initially 0. Arr is pointing to the same array which was there in the main function. Now, time complexity is the time taken by the function proportional to the input. Similarly, memory complexity is the memory taken by the function proportional to the input. Here, we have array as input. If you know a little bit of programming, then the entire array is not passed here. Only the pointer to the first element of the array is passed, irrespective of the programming language. So even if we are using Java, in Java, this array will get created in the heap area. And this arr is just a reference to this array in the heap area. So in any case, what is the extra memory taken by this function? So this function has a reference arr. It has an integer variable n and integer variable I. Even if you have array of size 100, there will still be these three variables. Whether the size of the array is 0 or 100 or 10 or 50, the memory footprint of this function is constant. So memory of this function is constant, and the time taken by this function is obviously order of n, because there is the for loop which is iterating over all the elements of the array. Therefore, in terms of time, this function is taking order of n time, because the time taken by this function is dependent on the length of the array. But the memory taken by this function is not dependent on the length of the array. You should not get confused by this arr. Arr is not the entire array. Arr is only a reference to the array. And reference takes constant memory. In the language of C++, we can say that arr is just a pointer. So had it been a C++ function, we would have passed the parameters like this: integer pointer arr, comma, integer n. Because it is a Java function, so the syntax of Java is different. But essentially, arr is still a reference only. Arr is not the entire array. So the array is not passed as value, only the reference to the array is passed. And therefore, the memory taken by this function is constant. It does not depend on the array. Now let us change this function to recursively print the array. We have discussed in the reference video that recursion only handles one element at a time. We have to pass the index of the element that this function will print. Now, if you look at the signature of this function accepts an array of length n and index I. This function will print the array from index I going forward. Therefore, if the array is 5, 6, 7, 8, 9 and the index of the elements are 0, 1, 2, 3 and 4, if I is 1, then the responsibility of this function is printing the array starting from index 1, which means that this function will print 6, 7, 8, 9. If I is 2, then the responsibility of the function is to print 7, 8, 9. If I is 3, then this function will print 8, 9. If I is 0, then this function will print the entire array. Therefore, initially, you will call this function for I is equal to 0. Now, as you know that recursion only solve one layer of the problem and rest of the solution is delegated to recursion. So, this function will print the ith element of the array and then it will call the same function print array arr of size n starting from index I plus 1. When we call the function for 0, so this function prints 5 and then it calls the function for I is equal to 1, which will be responsible for printing 6, 7, 8, 9. That function will print 6 and then it will call the function for I is equal to 2, which is responsible for printing 7, 8, 9. That function will print only 7 and then call the function for 3, which is responsible for printing 8 and 9. So every function in this recursion is printing the ith element and delegating the responsibility of printing the entire array starting from index I plus 1 to the recursion itself. At one point we have to stop this recursion. We will stop this recursion when there is no element left in the array, which means that if I is greater than equal to n, that is the size of the array, it means there are no elements in the array and we'll just return from here without printing anything. Let us look at the call stack of this function. What this main function is saying is print the array arr of size 5 starting from index I is equal to 0. Let's draw the memory model again. So this is the memory model. First the main function will be called and main function has this array arr. In Java, this array will be created in the heap area. So this array 5, 6, 7, 8, 9 is in the heap area and arr holds a reference to that. So arr holds a reference to this. Okay, I am just removing this for the sake of clarity. Now the main function calls the print array function. When the print array function is called, then the stack frame of the print array function will be created. And this stack frame has arr, which is nothing but the reference to the entire array. Then it has n, which is equal to 5, which is the length of the array. Then it has I. Initially the value of I is 0. What will this function do? First it will compare I with n. So 0 is greater than or equal to 5? No. Which means that it will not return. The condition is false. So it will print the 0th element. 0th element will get printed. It means 5 will get printed. After printing 5, it will call the function for I is equal to 1. When it calls the function for I is equal to 1, I am not writing rest of the parameters because rest of the parameters remains the same. arr will still be holding the address of this array. N will still be 5. When I is 1, then it will print the first element, which is 6, and then it will again call the same function. So we have less space here. Let me shift the array up so that we have some space here. And I'm making this smaller. Then the function will be called for I is equal to 2. When the function is called for I is equal to 2, then it will print 7 and then call the function for I is equal to 3. Inside the function where I is 3, it will print 8 and then call the function for I is equal to 4. The function where I is 4 will print 9 and then call the function for I is equal to 5. Finally, the function where I is 5 will return, then this will return, this will return, this will return, this will return, and finally this will return and control will go back to the main function. Let us see it in the code also. Alright, so I have replaced the code and let's debug the code. We have put the breakpoint. Function stops here. Then let's go to the next statement. Let's call the function. So the function is called. Now in the stack frame, there are two functions, print array function and the main function. Inside the print array function, value of I is 0. If we move forward, then it will print 5. So 5 is printed here. You can have a look at the output window. The terminal, this is the terminal. So 5. At the bottom of the terminal, you can see 5. Then if we step into further, now in the stack frame, there are two print array functions. So in the first print array function, which is called by the main function, value of I is 0. But in the second print array function, which is called by the first print array function, value of I is 1. What will this function do? This function will print element at 1, which is 6. So after printing 6, it will call the function for I is equal to 2. Now there are 3 instances of this print array function. Okay. In the third instance, value of I is 2. In the second instance, value of I is 1. And in the first instance, the value of I is 0. You can assume that if the size of the array is 100, then the function will be called 100 times. And every time the function is called, a stack frame of the function will be created. And that stack frame will consume constant amount of memory because that function will have its own local variables. How much memory is this print array function taking? Memory taken by this print array function depends on the length of the array. And because it depends on the length of the array, therefore the memory complexity of this function will be order of n because it is directly proportional to n. In the previous section, we learned recurrences also, and because this is a recursive function, we can talk in terms of recurrence equation also. If the memory taken by this function is t of n, remember now we are not talking about the time, we are talking about the memory. If the memory taken by this function is t of n, then the memory taken by these two statements is constant. This statement is a function call with parameter n minus 1. Why we are saying n minus 1? Because we are starting from I plus 1th index and not from ith index. So this will take t of n minus 1 memory. The recurrence for memory complexity of this function will be tn is equal to t of n minus 1 plus constant. And we have seen in the previous lesson that the solution for this is big O of n, because you will end up adding 1 n times. You can solve it using either the substitution method or the function call tree, which is nothing but the memory model. Consider this function. We have already seen this function. This is a case of infinite or non-terminated recursion. Because the recursion is not getting terminated anywhere, so this function will keep on calling itself. First the main function is called, and then the main function will print hello, and then call the main function again. So in the memory model, you can see that first the main function is called, this main function prints hello, and then call the main function again. This main function will again print hello, and then call the same main function again. That main function will print hello again, and then call the same main function again. And this will keep on repeating infinitely. Ultimately, at one point, the memory stack will overflow and the function will crash. So we can say that this function requires infinite amount of memory if we do not want it to crash. You can also say that the time taken by this function is also infinite because it will never stop. Both the time and memory complexity of this function is in a way infinite, which is obviously not possible in computers. So whenever the memory stack exhausts, this function will crash and stop executing. Compare it with the second function. Now in this case, we do not have recursion and the main function is called only once. If the main function is called only once, then there will be only one stack frame of the main function. There will be only one instance of the main function inside the memory stack. And that stack frame of the main function will keep on executing infinitely because we have this infinite while loop. The condition of the while loop is always true, and therefore it will keep on printing hello infinitely. So unless we explicitly kill this function will keep on printing hello. From the point of view of time, this function is taking infinite time because it will never stop on its own. But from the point of view of memory, we can say that the memory taken by this function is constant because there is only one stack frame of main, and that stack frame will take constant extra memory. So memory wise, this is a constant memory function, but time wise, this is infinite time complexity function. While finding the time complexity, we saw that there can be multiple time complexities starting from constant time complexity to factorial time complexity. So the time complexity of a function can be big O of 1, big O of log n, big O of n, which is linear, big O of n log n, linear arithmetic, then big O of n raised to the power 2 or n raised to the power 3 or n raised to the power 4, which is polynomial time complexity. Then you can have big O of 2 raised to the power n, which is exponential time complexity. Then you can have big O of n factorial or n raised to the power n, which is factorial time complexity. Now the same is true for memory complexities also. The memory complexity can be constant, it can be logarithmic, it can be linear, it can be linear arithmetic, it can be polynomial, it can be exponential, or it can be factorial memory complexity. And what was true for time complexity is also true for memory complexity. In memory complexity also, you can have recurrence equations and they will be solved in the similar way the way we solve them in time complexities. Similarly, the way we can have a time complexity, which is the combination of these time complexities, we can have a memory complexity, which is a combination of these memory complexities. Next, we will look at some of the practice questions related to memory complexity.